Okay, thanks everyone for choosing this session, and thanks to the organizers, of course, for everything. So, can everybody hear me? Is this working fine? Okay, I've written a book that I've just put in the archive a couple of months ago, and it's called Minotaurus of High Categorical Diagrams, and it revisits all the kind of classical topics about pasting diagrams from the kind of 80s, 90s papers by Street, Steiner, Howard, Johnson, and others, from kind of trying to put some order into that and add a little bit of the perspective that we have developed over the last 30 years. And so this talk is kind of meant to be an introduction both to the book and to the kind of aspects that are original to it. So the title says pacing diagrams. I have to warn you that I'm using pacing diagrams in a different, more general sense to the one that they were used in the talk by Ioannis Markakis in the previous session. And I also make a distinction between pasting diagrams and just diagrams. I'll tell you a bit more about it later. So what is a diagram in an N category? Well, this is one of those concepts that kind of live at different levels of formality at the same time. So, well, first of all, one says a diagram, for example, two-dimensional diagrams, we think of some kind of picture which may look like this. This could be something that lives in any two category. So this is the kind of intuition that we're trying to capture. And then there's a kind of first level kind of trying to turn this formal, which is going towards, okay, what is it that this picture is representing in a kind of, as a concept rather than as a specific mathematical object. And my answer to this would be that, well, first of all, this is a drawing of a cell complex in the combinatorial topological sense. We've got some zero-dimensional cells, some one-dimensional cells, some two-dimensional cells here. But that's not all it is. It also has this direction where we're not just having kind of topological cells, but we're also saying that every cell has a source and a target, or an input and an output. And by a direction, for me, is a specific kind of orientation which consists of subdividing a cell in a cell complex is a topological ball. Its boundary is a topological sphere, just one dimension down. And the direction can be construed as being bipartition of the boundary of this sphere into two halves, one of which we treat as a source or input boundary, and the other one we treat as an output or target boundary. And then furthermore, there are also these labels, and the idea should be that these labeling defines a map, or defines, in the case of N categories, defines an N functor. So overall, we got some kind of directed cell complex. This thing is, we need to have some kind of interpretation of this directed cell complex as some object, as some high categorical structure which is generated by these cells, and then we have some kind of labeling, or we want to know that this labeling in kind of cells of some high categorical structure defines a unique N functor. So this is the idea. It's a model-independent idea, the same way that cell complexes are more than any kind of instantiation of what a cell complex is mathematically. And to kind of try to capture this idea, several mathematical structures have been proposed over the years. Go by the name of parity complexes, Ross Street, pasting schemes, or directed complexes. And all of these can be seen as kind of particular models of this concept, or at least of the part which kind of relates to just the shape of a diagram without prior to its labeling. And so these kind of mathematical structures, you can say that they always consist of two parts. There is some kind of underlying data structure which is trying to just encode the object as some kind of mathematical object, and kind of roughly these can be split into three kinds. The most common is a kind of combinatorial data structure, which usually is some kind of poset-like structure, which is trying to encode the cell complex by its poset of faces, sometimes called the phase poset or incidence poset, and then kind of complement that with some data defining an orientation. And kind of combinatorial approaches like this are the one by Street, by Johnson. Steiner has two kind of different approaches. The one in the 1993 paper is of this kind, and there is also a kind of more recent kind of paper by Forrest that both kind of compares some of these models and gives a kind of improvement on Street's original definition. There have been also approaches which are topological in nature, like really trying to capture these objects as topological self-complexes together with some embedding in some particular embedding in Euclidean space, for example. This is the approach given by Power in his original categorical pasting theorem. There's also a paper by Kaprano-Levalsky that looks at kind of an orientation defined on actual convex polytopes embedded in Euclidean space. And finally, there's also something that's been kind of particularly popular in recent years. There's this algebraic approach based on chain complexes together with some extra data pioneered by Richard Steiner in a 2004 paper. So that's at the level of what the underlying data is, and then this is usually complemented by some characterization of what the well-formed structures are amongst the ones here. And I would like to subdivide these two into kind of two different approaches. There's a kind of synthetic approach where one tries to define for example, the composable diagrams. I'm going to tell more about that. By specifying kind of constructors, or giving kind of an inductive definition of what the well-formed structures are, so that being well-formed means being generated by these constructions. And that's kind of pretty much, I think, confined to this 1993 Steiner paper, which I mention here because it is the main influence of what I'm going to talk about. Whereas most of the other approaches are, let's say, of analytic type, in the sense that they try to characterize well-formed structures by axioms. So by saying, if you take one of these underlying data, if it satisfies a list of axioms, then it is well-formed. So it is actually defining a diagram. So again, I'm making a distinction here between diagrams and pasting diagrams. It's not standard terminology, just something that I found useful. So among kind of diagrams, they're kind of usually in defining what a well-formed diagram is, it relies on defining what a pasting diagram is. A pasting diagram is a diagram which admits a composite. So the idea is that a diagram consists of multiple cells. A pasting diagram is a diagram for which these multiple cells admit a composite, so a single cell which somehow arises from the compositions of all the cells that are contained in it. So, for example, this in one dimension, this kind of basically a linear graph will be pasting, in the sense that this admits a single composite in one category, but something like this is going to be non-pasting for more than one reason. So for me, a diagram is not necessarily a pasting diagram. A pasting diagram has a composite. So, I was saying that this characterization of what the well-formed diagrams are, I think that pretty much all of the approaches that I mentioned before include among their axioms some kind of acyclicity condition. So what happens in these diagram shapes that the orientations defines a certain kind of flow between cells, right, where you can kind of go from an n-dimensional cell to its output boundary and then from the input boundary to an n-dimensional cell. And then what most of these axiomatizations have is to say, okay, that this flow in any dimension, so taking the flow through n-dimensional cells for any n, is going to not have any cycles. So again, there are different acyclicity conditions that have been considered, some of them stronger, some of them weaker, but all of them bar at least this kind of, like at least the usual cycles that we know from directed graphs. These structures cannot appear in well-formed structures in pretty much all of these approaches. And so one can ask, why is it the case that acyclicity conditions are imposed? So I would like to suggest that there are three main motivations, and I'm also going to rank them by how valid I think they are going to appear at the end of the talk, hopefully. So the first one is that, especially in these kind of analytic approaches, one is trying to kind of carve out the well-formed structures among all the structures. Kind of acyclicity is a kind of, it removes a large chunk of kind of bad examples, like saying, okay, well, if we impose acyclicity, we've already gotten rid of many of the kind of unwanted pathological cases. So it's for kind of this reason. Right? So we impose it because it works in getting us, ridding us of things that we don't want. The second motivation is that usually the way that these approaches go from this data structure to defining some kind of n category is to have this n category consist of kind of subdiagrams or subsets of cells that are of a particular kind. And acyclicity in this case is what kind of enables one to represent every kind of cell in the n category kind of generated or presented by this diagram as a subset. So, for example, in this case, in the free category on this graph, for example, there are cells corresponding to traversing this loop any number of times. All of these, in terms of kind of cells in this cell complex, contain just this one and this one. So just saying what subset of cells appears in this path is not enough to separate these different cells. And the third motivation, which I'll mention, is the one that I think is actually a kind of a good motivation as long as one cares about this, is that acyclicity seems, and it appears to be related to the property that the presented n category is freely generated in the sense of computats or polygraphs. So I don't have an allegiance to either polygraphs or computats, so I'm going to use both terms interchangeably. So these are motivations for acyclicity, but acyclicity has downsides too. Now, first of all, it excludes, as I said, it excludes bad examples, but it also excludes plenty of good examples. So, in case of non-pasting, already in dimension 1, we have diagrams that we certainly, if we draw this kind of diagram in a 1 category, we certainly can assign a meaning to this univocally as corresponding to a functor from the free category in this graph to a category. There is no problem with that. So we may want to have this in our kind of class of well-formed structures, but it is not going to be an example of any of these kind of approaches, and the theorems that are proved for any of these approaches are not going to apply to this. And even if we are only interested in the pasting diagrams, we are okay with acyclicity up to dimension 2, but in dimension 3 there start appearing cycles, and not just in contrived examples, but in kind of naturally occurring ones. So in this example, the two sides of this kind of three-dimensional cell are one of the triangle equations of the junctions. Here, if we interpret these in the two categories, this could be this is a right adjoint functor, this is a left adjoint functor, and this is just saying that it's one of the triangular junctions. So either because we're trying to kind of capture this equation as being some kind of cell, or because we are actually working with pseudo-adjunctions of bicategories, for example, we may want to relax this equation into a three-dimensional cell. And the shape of this diagram now is not acyclic, because if you follow, like this point is the same as this point is the same as this point, so we go from here to here and then back from here to here, and that this is exactly this loop. So these are kind of naturally probably one of the first kind of three-dimensional cells that somebody could see in appearing in nature, and it's not acyclic. The second kind of problematic thing about acyclicity is that it's a global property, and global properties tend to be very unstable under constructions and operations that we want to perform. So, in particular, there are different kind of flavors of acyclicity properties, but the stronger ones tend to be not stable under taking duals or what is called opposites. So, if we just reverse the direction of cells in some dimension, we may start from something acyclic and get something cyclic. For example, there are some dualities even on streets-oriented syntheses which produce something that's not acyclic, and in this stronger sense. And whilst the weaker acyclicity properties, they tend to be stable under duals, but they're not stable under other operations that we want to do on pasting grounds, such as grade products. Well, just the forming of pasting composites of pasting diagrams, or ancategorical joints, such as studied by Dimitriara and George Matsignotis. And in addition to this, there is a certain sense that I've only learned last week from Guillaume Laplante and Fossi. This is a forthcoming work together with Medina Mardones and Padral. So they've also been looking at kind of acyclicity on kind of orientations which are of this kind of Kaprano-Vygotsky type, which is induced by orientations on convex polytopes. And so something that they've proven is that if one looks at the density of the directions that one can, if one looks at all the directions that one can put on n symplecses that are well formed in the sense that they do define some kind of pasting diagram structure on an n simplex, then the density of the acyclic ones tends to 0 as the dimension goes to infinity. So street-oriented syntheses are acyclic in a very strong sense, but they are the outliers. Most oriented syntheses are not going to be acyclic. So, yeah, acyclicity is rare. So, something that I tried to do for several years, and then in this book, is to develop methods of just saying, okay, cycles are just there, they're not going away, so how do we live with cycles? So the first idea is that instead of kind of having acyclicity as a property that we require for our backbone structures, we replace it with regularity in the sense of regular cell complexes. So regular cell complex is one in which the attaching map of any cell is an embedding. So basically, a cell is a mapping of an n ball into a cell complex, and in a regular cell complex, this map is always an embedding. And so, in particular, in the directed world, we have something a bit stronger as a form of regularity, which is not just to say that the boundary of an n cell has to be an n-1 sphere, but also to ask that both the source and target halves of the boundary are going to be close topological n-1 balls that intersect in their boundary. And this can be captured combinatorially by the condition that the k-dimensional, for every k smaller or equal to the dimension of the cell, the k-dimensional target boundary and the k-dimensional interboundary have to be equal to the union of the k-1 dimensional source and target boundaries. This has been considered also by Simon Henry and others. So, regularity is a very beloved condition in combinatorial topology, precisely because it has lots of good properties. It is local. It is stable under all sorts of constructions, and even in this directed world, it turns out to be stable under all the constructions that I've mentioned before: gray products, joints, pasting, suspensions, and so on. And topologically, it's what ensures, like it's well liked because it seems to be the kind of the widest conditions which ensures that a cell complex can be studied fully combinatorially from its phase coset. A regular cell complex can be reconstructed uniquely up to homeomorphism from its phase coset. So it's kind of guaranteeing that we can still get back to our picture from our combinatorial structure if we take one of these combinatorial approaches. So that the argument here is the regularity kind of works better than explicitly reading does of bad examples without getting rid also of good ones. So for the second kind of motivation, the idea here is that if one looks at a directed graph G, one can see that if one asks that the linear subgraphs have to form a category, that will only be true if the graph G is acyclic. However, one can always get a free category on the graph by taking paths in G, and paths can be seen as more general morphisms, more general graph homomorphisms from linear graphs onto a graph. So the suggestion here is that if we want to still get an M category without acyclicity, we have to move from just considering subsets of cells to considering morphisms of diagrams. And so the solution here is given by considering this category of whose objects are oriented graded cosets. This is this kind of phase coset plus orientation structure. It goes by several names in the literature, but essentially the oriented graded coset is a graded coset, so a coset in which elements have a certain rank or dimension given by how long the chains under them are. And an orientation is given exactly by a bipartition of the set of faces of every element, that is, of the elements which are directly covered in the coset into two disjoint subsets called output faces and input faces. And then as morphisms of this category are considered functions between the underlying sets that, so for every element X, I ask that this induces a bijection between between the sets of input faces of X and the input faces of Fx, and between the output faces of X and the output faces of Fx. So this category has at least some nice properties, including the fact that it has push-outs of injective morphisms along injective morphisms, which allow us to glue together things. And then what we do is define a subclass of these oriented graded cosets which are going to correspond to these shapes of pasting diagrams. These are called molecules. This is adopted from this Steiner 93 paper. It's very close to what was done there. And so the constructors for molecules are just given by three clauses. The first one says the point, which is just a graded coset with just a single element, is a molecule. This one says that essentially the molecule, the shape spacing are enclosed under globular pasting, because what we get just from the structure of oriented graded coset is a combinatorial definition of k-dimensional source and target boundaries. So this is saying that gluing two molecules along some isomorphisms between the target K or let's say output K boundary of one and the input K boundary of the other one, which is a globular pasting, will produce also a molecule. And the third condition tells us now, it has this restriction that if U, V are molecules, they have the same dimension and they are round, which is that condition that I mentioned before. And also I have some isomorphism between their entire boundaries that kind of is compatible with the orientations. Then I can kind of glue them together along their boundary, which again is a push out in this category. And then I can add some top dimensional, some greatest element to the poset obtained like that, and say that U is going to be now the source of this, and V is going to be the target of that, and that produces another n+1 dimensional molecule. So again, molecules have lots of nice properties. They are rigid. They don't have any non-trivial automorphisms, which also ensures that in the previous slide, when I said along an isomorphism, it's always going to be unique. So it's independent of what isomorphism we choose. Again, they're stable under pretty much anything that you can hit them with: boundaries, pasting, suspension, gray products, joints, and duals. There is a notion of geometric realization of our integrated poset, and all molecules are realized as some generalized wedges of closed topological balls, and they're particularly all contractible. And the most important thing is that the isomorphism classes of molecules in this category form a strict omega category with this pasting, with this universal pasting operation, this K composition. And it serves us well that pasting here is defined by universal property, because it allows us to descend to slices over any orientated poset and say that basically just by taking kind of fibered, very simple fibered versions of the theorem that I gave before, and say that these kind of isoclasses in the slice over P of morphism from a molecule to P will always have a structure of strict omega category with this fiber pasting, this composition. I'm almost finished. I have only a couple more slides. And in particular, if one restricts to this class that are called regular directed complexes, which are your integrated posets such that the lower set of every element is a molecule, then which is something that also, for which we can also prove that the underlying poset on any such regular direct complex is the phase poset of a regular CW complex, so this truly is a kind of directed version of a regular cell complex. Then, in fact, this omega category is generated by the inclusions of these lower sets into P for every X. In P is composition generated by this. So it has the property that we expect that this omega category is generated, like that its generators are in bijection with the cells of our cell complex. So I was just going to say two things about kind of the third motivation, which I said was the one that's valid, because what we do lose by kind of generalizing is that this omega category is not in general going to be freely generated. So acyclicity does play a role in free generation. However, what this is actually joint work with my student Jana Kessler. We've been studying kind of how one can get some milder conditions that ensure this property, and in fact, this kind of full-blown acyclicity that has been considered before is not necessary. It is there is a milder technical condition that we call having frame acyclic molecules, which is sufficient to have these free generation properties if one wants it, and this turns out to always fold up to dimension 3. So we can say that if the dimension of an reintegrated poset is smaller or equal than 3, then this omega category is going to be a polygraph or a computat. So we're kind of in the best of all possible worlds up to dimension 3. So yeah, the final message of this talk is that you can stop worrying and learn to love cycles, and if you absolutely need to get computats for strict linear categories, you can still embrace all cycles of the dimension 3, and if not, you can embrace them in all dimensions, and I'm finished.
Firstly, thanks for the talk. It was very interesting. My question is regarding your notions of computats, because if we wanted to think about, say, even in dimension 3, uniform interchange for two-dimensional data holding or not, then there's a difference between, so there are 3 computats.
So in this case, I'm talking about computats for strict M categories.
Right.
So I'm not, yeah.
Okay, let's take Amar again.